There we go. 16. The volume of an expanding sphere is increasing at a rate of 12 cubic inches per second. When the volume of the sphere is 36 pi cubic feet, how fast is the surface area increasing? And they give you those formulas. Okay, so the volume is expanding at this rate. So what is that? That would be V prime. Would be 12. And it's increasing, so we know it would be positive. So V prime. So I would write that as 4/3 pi r cubed. So I need to do the derivative of that, and so that would be V prime would equal, bring the 3 down in front, that would be 4 pi r squared times r prime. And we know that that equals 12. And it says it is, so that must be doing that all the time, no matter what the radius is, or doesn't it say? Oh, right here. When the volume of the sphere is 36 pi cubic feet. So this is increasing at that rate all the time, no matter what the radius is. Okay? So at that instant, what we want to do is figure out what r prime is. So when we want to set this equal to 36 pi. Okay? So when the volume is 36 pi, so the pi's would cancel. Let's see, if we multiply by 3/4 to cancel that, that would be what? 4 into 36 is 9. 9 times 3 is 27, because this is all no calculator, right? So r cubed is 27, so r would equal 3. So we know r would equal 3. So 4 times pi times 3 squared would be 9, so this would be 36 pi r prime equals 12. So at that instant, r prime is 12 over 36 pi, right? So I knew the volume was 36 pi, so I set that equal to the volume equation. I find out that r is 3. Then I know that v prime is 12, so there's my v prime equation. I put a 3 in for r. I find r prime to be that. Okay, how fast is the surface area increasing? So the surface area would be S prime, so we'll bring a 2 down in front. That would be 8 pi r times r prime. I know that r is 3, and I know that r prime is 12 over 36 pi. So 3 would go into 36. That'd be 12 times 12 would cancel 12. Oh, yeah, I could have reduced that. That was silly. Yeah, that's 1 over 3 pi. But anyway, so 12 cancels that. The pi cancels the pi. Oh. 8. So did you do it another way and got that answer? Oh. In terms of v, sure. Because solve this for, it's like 2 equations, 2 unknowns. You get s in terms of v. They do, and then to find s prime, you do the derivative. That would have a v prime in it and a v. You know you can put v 36 pi in for v. You know you can put 12 in for v prime. That's a great idea. Now, it gets into cube roots and 1/3 powers and some ugly, messy stuff there. Did you get the right thing? Yeah, it should come out. If you don't make any mistakes, it should. That's not a bad idea. It's just that we worked with this before where we didn't really do that, right? We just took that, we did the derivative where it was, and we had several equations we worked with at the time and substituted things in and so forth. But that would work. Yep, that would work. 21. Now, we may take some time later in the week to answer a few more in this section. So if you've got some. Oh, now does this look familiar? Good. Well, this will be good. This will be a good lead-in today because on Thursday, if you were gone, now there's a video from Thursday, and it's quite awesome, if I do say so. There's a video from Thursday. There's notes from Thursday. Okay, so if you were gone, those are up there. It says a solid has a circular base of radius 3. Now, I think maybe what's the hardest part about this is they didn't give you an equation, and you have to do that yourself. So if you have a circular base radius 3, then what you need to do is you need to make that yourself and know that that would be the equation x squared plus y squared equals 9. Right? And the problems we've been given has been there's a region, okay, the region is the base of a solid and then the cross section and then coming up off of that base. So this is the one we did in the picture. Matter of fact, I can even remind you guys of that, anybody who wasn't here. It's basically this problem here. Here's the circle, right? And we're going to have equilateral triangles coming up off of the circle, creating a solid, right? And that's what we're talking about. Instead of revolving a solid, we're talking about having a base coming up off here. Now, the difference is most of the time you're given the equation that you're supposed to use. In this problem, they didn't. You had to come up with that yourself. And so that's the key. And so when you solve that for y, you get plus or minus square root of 9 minus x squared. It says the cross sections are perpendicular to the x-axis. It will always tell you that in these problems. It'll tell you what direction. So you draw in your strip. So now we're going to have, now this problem is actually more like, equilateral triangles, right? So equilateral triangles. So here's your strip right along here, right? What is the strip? It's one side of your equilateral triangle, right? And in our notes the other day, we had these formulas right here, right? These are the types of slices we're going to have to deal with. We're going to deal with square slices, equilateral triangle slices, or semicircle slices. So these are equilateral triangles. So that strip that I drew is one side of the equilateral triangle. So that's the formula I need. And then I just put it into this integral right here. But Keaton, that was it, right? Yeah. The issue is this. But again, this is a nice review. So the top half of this circle is the positive square root. The bottom half is the negative. So this strip would be square root 9 minus x squared minus negative square root 9 minus x squared, which of course would simplify to 2 square root 9 minus x squared. So that's our strip. So the integral would be root 3 over 4. The integral of this squared, correct? Right, because that's a formula for an equilateral triangle. The area of an equilateral triangle is square root of 3 over 4 times s squared. And then the integral adds up. Now, have me run these maintenance things. Okay. All right. So anyway, 17. Okay, and those are square brackets right there. And f of x is this, so I think you would just substitute, wouldn't you? Oh my gosh, I thought that was absolute value. I did too when I first read it, and I thought that's going to make it interesting. Yeah, those are just little square brackets.
Well, in that case,
okay. Well, so then it'd be 15 minus g of x would be 15 minus 2g of x. And then, yeah. So if you split this apart, this would just be a 15, line of 15, negative 2 to 2, so it'd be a 4 by 15 rectangle. So that's where the 60s come from in all those. So it'd just be 60 and then minus 2 times the integral. So this one down here, e. I would agree. All right. The other class asked about one of the earlier ones, like number 6. It was an absolute value. That's what made me think of it. There's this absolute value one. What did you guys do on that one? It was number 10 or 9. Yeah, that's the key. It's just geometry, right? That's what you want to do there. You're not trying to do an absolute. As a matter of fact, we've rarely done an antiderivative on an absolute value. What you want to keep in mind about an absolute value is where it crosses the x-axis, the function just turns opposite. So if you wanted to do an absolute value on this, you could, but you still would have to graph it, I think, because you still have to understand that it's shifted left too. So the integral from -2 to 3. The integral from -2 to 3 would just be this plane integral here, and you could do it. You could just do a straight antiderivative if you want. But from -3 to -2, what's the function? It would be the opposite of x plus 2, right? I mean, that's how absolute value works. It takes anything that's down here and flips it up here. Well, that makes it opposite. So you can do it this way, as an antiderivative and as an antiderivative, and get your answer. But I think the easiest thing to do is just break it into a couple of triangles, right? You got a triangle here, and just do it. It came out to that. So that would be my recommendation when you see an absolute value. Now, where that doesn't work as well is when you get like a parabola. I guess is the reason I'm saying that. Oops. If you get a parabola that's x squared minus 4, and then with bars around. Well, now when you go to graph that, there's your parabola shifted down, but then this part's going to be shifted up, right? So you got to know where it crosses, at -2 and at 2. And if they wanted the integral from -3 to 3, well, then you'd have to do the integral from -3 to -2 and get that piece. Then you could get this piece and just make it positive. So you could do the integral from -2 to -2, or you could flip it up and do it, and just know then that integral would be this, right? This part of the curve would just be the opposite of x squared minus 4. So sometimes you get them like that, and then they're not triangles where you just do geometry. So then you do got to kind of break it up, and then you can do antiderivatives in pieces. But anytime you have an absolute value, you're doing the integral. That's pretty much how you have to do it. All right, one of those two ways. All right. Well, let's stop there and let's move on to the new stuff we have to do today. And if we need to later in the week, have some others. But again, you're welcome to come in the morning and ask me questions. Check your answers in the book. That's certainly something you should try to take advantage of. All right. So here's some. I just kind of rewrote what I had in your notes the other day. I don't know that this is necessarily important to copy this down again, the way I wrote it here. Just trying to organize our thoughts here a little bit on this, but it's totally up to you. I am going to write something over here, a new formula. That connects to this here today. But first, I just wanted to review this idea. Now, since we did that problem 21, we've kind of done this a little bit already, so that's good. So earlier in the week, last week, on Monday, Tuesday, we had done these volumes of revolution. We did the slicing of the lemons and that whole thing. And so there's two types that are volumes of revolution. And they either have solid slices like the lemon did, or they have an empty space, and then they're a washer. And then we've got this formula. But the idea we learned is all we need to know is the area of the slice or the cross section. And then the dx is the width, which of course becomes paper thin and goes to nothing. But basically we have area times width, which is volume. The integral adds up the volume. So when we're doing slicing, this is the formula we follow. And we can have 5 different area formulas that we talked about. Now, we did say that there could be another type of formula. I think one of your homework problems had this, as a matter of fact. If your slices, well, let me back up. So we have our volumes of revolution are going to be one of these 2 types. They're going to be circle type slices. And then there's those ones on the base, like we just talked about. So if you have a base region and the slices come up off of the base, I told you you'd be responsible for these 3: squares, equilateral triangles, semicircles. Now, we did talk about, there was one on the homework where it said your slices were rectangles of height 4. I think it was. Rectangles of height 4. Well, we can do that too. What's the area of a rectangle? Base times height. Well, if the height is 4, just be base times 4. And what's the base? The strip, right? The strip. So whatever your strip is, that would be an angle coming up off the page, and then the height would be 4. So in your integral, you would just have the strip times 4. That's all you'd have. Okay? In these, the strip, for a square, the strip was the side of the square. In the one we did just a minute ago, the equilateral triangle, the strip was one side of the equilateral triangle. So we squared it, we had a root 3 over 4. And then we had the one with the semicircles. Maybe it'd be good to look at that again, real quick. In the semicircle one, okay, here's the strip. And the strip is actually the diameter of the strip is right here. It's actually the diameter of the semicircle. And so that's why we have this formula down here, 1/8 pi times the diameter squared. So the strip is the diameter when it's a semicircle. It's a side of the equilateral triangle. It's a side of that. Or it's a radius, or the strip. We draw in the strips, we have the outer and inner radius. So those are the problems we've done so far on volume. Okay? So before we do the new one, we've already done an example of one of these. So I want to go back and do an example of one of these, volumes of revolution. So let's go back to, let's go back and in your notes or just on a piece of paper somewhere, you don't have to be in your notes, but wherever. Let's do that problem right here. By yourself, with a partner, talk it over, whatever. Let's find this volume. Now here's the region. The top line is the region. And then we're going to revolve it about that line right there, x equals 5. Let's see how we do on this one. help each other out if you got, if you're not sure what's going on, what to do. Ask a neighbor. What are some of the issues? Or not issues, but what direction are the strips? Have to be horizontal strips, right? Have to be. If you got a vertical axis of revolution, slices have to be perpendicular. What else? There's empty space. So it's going to be the washer formula. What else isn't? That's okay.
The big radius changes.
So what do we have to do? Split it up. You have to split this into two regions. Right? Nod your head. How many? Have we got an answer then? Somebody? Anybody? What?
I got 370.
3. That sounds familiar from last block. 3 something. Now, Randy said it doesn't hit the function. That's right. In the bottom part, it doesn't, but that's okay. Remember, when we do a horizontal strip, it's right x minus left x. So down here, the right x is 5, the left x is 1. No problem. Just 5 minus 1. Because really, what do you have down here? It's just a plain old cylinder, right, with some empty space in it. The bottom part, because the sides are straight. So the big R is 5 minus 1, the little r is 5 minus 4. Which is fine. Which is fine. You wouldn't even need calculus to actually calculate that. You could just do it as a cylinder inside of a cylinder. Okay? Outer cylinder minus the inner cylinder. But then here, the x coordinate is 5 minus this x coordinate. Whenever you do horizontal strips, you got to let x, you got to solve for x. Which can be an issue sometimes. But in this case, it's easy. So it's right x coordinate 5 minus left x coordinate, which is y squared. So it's 5 minus y squared. Right? Remember, if you do horizontal strips, you're going to have in terms of y. So I've got, and then the top one, this goes from the strips fill the space from 1 up to 2. Here the strips fill the space from 0 up to 1. We've got to split that into 2 pieces. And what did we say the answer was? 328 pi over 15. Vertical strips. Now, why couldn't we use vertical strips here? Yeah, it's rotating about a vertical axis. So, like we said, if you're revolving around a vertical axis, the strips have to be horizontal. The slices have to be perpendicular. You just got no choice. What we'd like to do is be able to have a parallel strip. If I've got a vertical axis, could I do a parallel strip? And the answer is yes. They won't be slices, however. Now, the book calls this the shell method. That's traditionally what it's been called. I like to think of it as wrapping or the layer method. But we'll call it shell method too. But it's basically layers. And the idea is this. Think of the lemon. If we could take the lemon and we could just somehow peel an outer layer off of the lemon. Have a lemon-shaped peel. And then peel another layer off, and another layer off, and another layer off. See where I'm going with it? And we could add up the volume of each of the layers. That would also give us the volume. So instead of slicing the lemon this way, if we could think of peels, or excuse me, layers that are peeled off and added together, we could do it. Now, I used to have a thing. Somebody stole my toys. One of those. Somebody in the art class called it a Russian doll, like one of those Russian dolls. Like the barrels. I always think of the barrel like what I had was this like barrel. You opened it up and it was a little barrel inside, and another one inside of that, another one inside of that, another one inside of that. Right. That's what we're talking about. Layers around layers around layers around layers around layers. And if we could add up the volume of those layers, we could do it. And the nice thing about that is that would do what we want. If this is the axis of revolution, we could have an inner layer, and a layer around that, and a layer around that, and a layer around that. And they would be cylindrical shape because we're still revolving. So we would create, I'll show you here so you can visualize it here a little bit. It would, so if I took this region, so here's the region we just got to do it, but now I've got a vertical strip in there. So if I would revolve this, okay, so here's my solid, and now you can see that we've got this kind of cylindrical shaped layer, and if I sweep those through, you could see the different layers. Okay, it would be a little bit like this. It would be, okay, here would be our lemon situation. So here's like x equals 5, right? So this would be a situation where we're taking the lemon and setting it up on its end. Okay, and what we have been doing is doing this, right? We've been slicing perpendicular. And we've been getting a washer, or if there's no empty space, a disc. Okay, that's what we've been doing up till now. But what we want to do instead is think of it this way. okay? Where this would be one layer. Now notice, we make, when we do our slices, right, we end up making our slices infinitely thin, like paper thin, and we would want to do the same thing with our layers, okay? But in the beginning, we would have, like we did with a lemon, we'd have these thicker slices, but this width would go to nothing. This would be the dx part right here, but actually dy, since it's horizontal. Same thing with this red strip right here. Our strip would be this part now. Not our radius. See, our strip was like our outer and inner radius here. Our strip is actually going to be the height of this cylinder. Okay? So what we need to do is we need to come up with, for our formula, for our equation, we need the volume of this cylinder. Well, how do you do, and I'm talking about the solid part here, right? The blue solid part of this. Well, how do you find the volume of something like this? Now, how do you find the volume of a cylinder with empty space in the middle? The outside cylinder volume minus the inside cylinder volume, right? That's what I need to do. I need the outer cylinder volume minus the inner cylinder volume, and that will leave me the ring-shaped solid, and then we'll use the integral to add up all the different layers. So that would be one layer. So we want to write the volume of one layer. So this is what we want to put in our notes here. I think it's worth writing out. So I've tried to draw the picture here, so you can if you want to. This was like the red rectangle that we just saw a minute ago. And this would be like one cylindrical layer. This is often called the method of cylindrical shell. So what they're calling that is a shell. That's one shell, and then another shell inside of it, another shell inside of it, that we create the solid. Okay, so that's where the name shell method comes from. Okay? Now, the axis of revolution would be right down the middle here. Okay, here would be your axis of revolution. Okay, right through there. And remember, this width, this width right here is going to be the delta x. That's going to be the part, that width right there is going to be the part that becomes the dx when we add this up. So this is going to be a little different because in our other formula it was easy. We just needed the volume of that slice, and we just did the area of the slice, and then the width was our dx. And that's how we got our dx in the end. Well, this is going to be a little different because you guys told me it's the outer volume. Well, that'd be pi r squared h. Let's use big R. See, that's the volume. That's the volume of that outer cylinder. Is pi times the radius squared, the outer radius squared, times h. This would be h right here. Minus pi little r squared h. See, the problem is I didn't use delta x there at all. See, in our slicing method, it was easy because we did the area times the width, and the width was the delta x, and so it was automatically in there. So before I can stick an integral around this, I've got to have something that's going to turn into the delta x, or the dx, when this gets thinner and thinner and thinner and thinner. That's the dilemma. So, here's what we're going to do. We're going to call this, I'm going to put a little line here right in the middle of that strip. Now remember, this strip's going to get really narrow, and the middle won't even matter at some point. But right now, I'm going to put a line right there. And I'm going to call from here, from the center to there, I'm going to call that P. Just because that's what all the books use. We're going to call that P, and we're going to write this in our notes here a little bit later, what P is. But P is from the center, which, when by center I mean axis of revolution. P is going to be from the center to the middle of the strip. Now, as that strip gets narrower, 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 the middle doesn't really matter. Okay? All right, and H, of course, we know is the height of our strip. Right? The height of our strip. Like that. Okay, that's what H is. All right, so now, let's come back to this. So I look at my formula. for my volume. Now this is just one layer, right? The integral is going to add them up. So this is the volume of one layer. Now I need to get delta x involved somehow. Well, and I also want h. So h, that'll be fine. That'll be the length of my strip. So I want h, so that's fine. But I don't want those r's in there. So how can I take big R out and get delta x in somehow? What's another name for big R there? Using these two. P plus what? 1/2 delta x. Isn't that true? Isn't that what big R would be? Because remember, I said P was from the center to halfway across the strip. So big R is going to be P plus half the width. Now what's little r? P minus half the width. Now, this is important because what's going to happen as the strip gets thinner and thinner and thinner, which it's going to do, what happens to big R and little r? They get closer and closer to being the same thing, right? Because as it gets wafer thin, and that's what we said, we're doing, just like with our slices, as they get wafer thin, there almost isn't a volume. It's like we said, we take a piece of paper, is this three-dimensional? Well, yeah, it is. There is a width there, but it's just very, very, very tiny. It's kind of the same thing going to happen here. All right, so let's rewrite this. So I'm going to put pi, and in place of big R, I'm going to put P plus 1/2 delta x. That'd be squared times h. And then I'm going to have pi, in place of little r, I'm going to have P minus 1/2 delta x, all that squared, and then times h. Okay? So this is the volume of my layer, the volume of my shell. Now I'm going to FOIL that. Nice things are going to happen. So I FOIL that, I get P squared. Now when I FOIL this, I'm going to have the outer times inner, that's 1/2 P delta x, and I double that, so I have two of them. So I'll just have P delta x. And then the last times the last, that'd be 1/4 delta x squared. And then I'll have an h there as well. Oops, that's on the outside. And then minus pi, then in parentheses I'll have P squared again. Now the outer and inner will be the same, but it'll be a minus, so that'd be minus P delta x. And then when I square that last one, that'll turn into plus again, 1/4 delta x squared. And then I have that h on the outside. All right, everybody with me in that? Now, both of those have a pi and an h, so I can pull that out. I'm going to pull that pi and h out of there. And now what do I get? If I pull the pi and the h out of there, wait a minute. The p squareds will actually cancel. And what about the 1/4 delta x squared? They also cancel. And what do we end up with? 2p down, so it worked out really quite nicely. So actually that all simplifies down to that. And let's rearrange that a little bit into 2 pi p h, and the delta x is going to turn into dx, and throw an integral on there to add up all of the different layers, and there we have it. Very nice. But we're going to have to define what p and h are, and that we're going to have to get those. But think about where that came from. The reason I like to go through this is where did that come from? It came from the outer cylinder minus the inner cylinder. It's the volume of this layer. And then we add up all the layers. And we get that. But what we have to do is we have to define what P and what H are. Well, right here we can see what H is. H is the height of our strip. Okay? So that'll be easy. We've always done that. It's top minus bottom, right? Or if the strip's laying down, it's right minus left, because we can do that. We can do layers either way. In this problem, we're doing a vertical axis, and our layers are going like this. And our strip is vertical. But if you had a horizontal axis, and you wanted to do horizontal strips, you can if you want, right? The layers would go this way. as opposed to slices, which do this. Slices are perpendicular, layers are parallel to the axis of revolution. Now, on the homework, I think most of the problems you have to do the shell method. Then there's going to be some where you get a choice. Do it whichever way would be easiest. Okay, now, for example, on this one we just did, on this problem we just did here, we had to split it into two parts, and that wasn't very nice. Let's put this in our notes. This would be a good time to put this in here. All right, so this is an alternate form, only works with volumes of revolution. This wouldn't make any sense to do layers if you were doing one of these volumes on a base, because these are slices, okay? But this is an alternate to slicing, called the shell method, okay? Or shells as opposed to slices, or layers. I like thinking of layers better. All right, and so the formula is the integral 2 pi we usually put out in front, p times h dx. Now, let's write this out. H is the length of the strip. So H is the easy one. That's what we've been doing. The length of the strip. Top minus bottom, right minus left, whatever. P is the new one. Now, P is actually really easy, but it's confusing at first. P is the length from the center to the strip. And by center we mean axis of revolution. Just like what I told you, the radius goes to the center. The center means the axis of revolution. So the P, so that's the one we're going to have to work on. Okay? So H is the length of the strip, and P is the length from the center to the strip. And we're going to go back and do that problem we did a minute ago here and show you how this works. Then we'll do a practice one as well. All right? Now, if I go back and look at my picture here, all right, how would we write P? Well, notice that H is going to be a top minus bottom, but P is going to be a right minus left. They're both lengths. This is this length, top minus bottom. P is going to be a right minus left. So within the same problem, you're going to have that. When you find P and H, one of them will be a top minus bottom, the other will be a right minus left, depending on which way the strip is length. Okay, and that's the way that will work. All right, but it'll give us the volume because of the work we did here. We're finding the volume of that layer. All right, so let's go back to this problem right here. So let's draw that same picture we had a little bit ago. So we had y equals square root of x. Over here we had x equals 5. Here we had x equals 4. Here we had x equals 1. We were looking at taking this region. We were going to revolve around x equals 5. But now we've figured out that we can do a vertical strip in that region. Right? Because, and again, you don't have a choice. You're going to have a choice whether you want to do the shell method or the disc washer method. But you don't have a choice which way the strip's lay. If you've got a vertical axis of revolution and you want to do shell method, then it's vertical strip. Okay? All right. So, that tells us H for sure. H is what? Square root of x, top y value, square root of x, minus bottom y value, 0, right? What is P? What's that? It is 5 minus something. It is 5 minus. How far is the strip away from the center? Well, it depends where the strip is, right? If the strip's over here at 1, how far away is it? 4. 5 minus 1. If the strip is here at 4, it's 1 away. 5 minus 4. If the strip is here at 3, it's 2 away. 5 minus 3. So what is it in general? 5 minus x. In other words, think about this now. The strip is just setting on some x location when it's a vertical strip. Matter of fact, what I like to do is just when I have a vertical strip, I just label it x. Because that might be a 2.5. Its x location here might be 2.5. That's what x is. Now, what if you had a horizontal strip? What would you label it? Label it y. Okay? So this is how we get it. Now, here's what I mean by a right minus left. It's simply this distance right here. How far is it from the center to the strip? 5 minus x. What if the center was over here? At, say, -2. X minus -2, which would be x plus 2, right? It's always, here's a little secret about P. But P is always going to be x minus 2, 2 minus x, 5 minus x minus 7, maybe just x minus 0, right? It's always going to be that. It's never going to be sine of x or square root of x. It's never going to be that function. It's always going to be 2 minus x minus 2, 2 minus y minus 5, whatever. It's always going to be that way with P. So it really is quite easy to find once you just kind of get the thought of what you're doing there. So h is the height of the strip like we've always done, top minus bottom, that kind of thing, from the function, from the curve. But P is simply going to be 5 minus x. All right, so our volume is simply 2 pi P. Somebody type this in for me if you haven't already. P times h, so 2 pi P times h times delta x, the dx part, which is the formula we created back on that other page. And then what the integral goes from? What does the integral go from? 1 to 4. The strip fills the space from 1 to 4. While you're typing that in, I'll point out one other thing. You notice how we didn't care about the empty space? With the shell method, we did not even have to worry about the empty space. What took care of that? What took care of the empty space? The 1 to 4. We only went from 1 to 4. What if the region would have went all the way over here? We'd have went 1 to 5, right? If the region would have went all the way to the axis of revolution, our integral just would have went 1 to 5. The P and the H would have been the same. So another kind of cool thing about the shell method is we don't have to worry about empty space like we do disk and washer. So you can have a problem that might be a disk, might be a washer. If you do it one way, if you do it with the shell method, there's just one way to do it. And same answer, 328 pi over whatever, 15, whatever it was. We get the same answer, which we hopefully should. Yes, Keith. Oh, okay, right. So let's say it revolved around x equals 4. The strip still fills the space 1 to 4, but the difference is P would be 4 minus x. So we would get a different answer. It would be a different solid, right? And it's like we said before. The reason it's a different solid is this has to go out farther because of that empty space, so it creates more solid as it goes around. So the empty space does matter, right? And so if there was no empty space, we revolve around x equals 4, the P would be 4 minus x, and we would get a smaller answer because there'd be less volume. Yes? Well, what would be some reason? Well, here I think the shell method was preferable because what do we have to do on the other one? Split it into 2. So that time, horizontal strips, we had to split into 2. Another time might be if this would have been an equation that was impossible to get in terms of x or solve for x, then horizontal strips don't work. If you can't get x equals, then you can't do horizontal strips. So if you've got a vertical axis revolution, you'd be forced to do shell. And it can work the other way too, right? It can work the other way. If I'm revolving around the x-axis down here, I guess, does that answer that for you? I mean, so those are some things you look at. Now, to be honest, on the quiz, when we get to the quiz on this, and on the AP test, they never say one method or the other. Matter of fact, they don't even acknowledge the shell method, really. The shell method is just an alternate form. I think every problem they ever give you on the AP test would be okay to do disc washer. But I've seen problems on the AP test that were easier if you knew the shell method. So I like teaching them both. And on the quiz, it's not unusual for people to do it both ways, right? Just to double check their answer, right? Do it one way, do it the other. Now, if you get two different answers, you got to decide which one you trust more, and go with one of those. But I'll probably try in the quiz to give you one where shell might work better. That would be, but I'll probably on most of them I'll just say find the volume, and you get a pick, whichever method you want. Like I said, on today's homework, there's going to be 4 problems I think where they say you have to use shell. Then there's another problem that has 4 different options off of it, or 4 different problems off of it, and then you get to choose. You get to pick which one. Okay, so we get some practice with both of those. But I want you to do one from scratch here now as a practice one. Okay, so you guys do, there you go. You guys do that one. Right there. Okay? Take this region, the top 3 lines are the top 3 things. The top line here is the region, and then you're going to revolve it about y equals 4. Now, I want you to do shell on this one. Okay, no. I take it back. I want you to do it both ways. This one can pretty easily be done both ways. I'm not sure one is easier than the other. Kind of personal preference. But just for practice, I want you to draw this region, revolved about y equals 4, and do it both methods. Disc washer and shell. All right. Are we getting something? 224 something? Now the red, so here if you prefer vertical strips, right? I mean, that's a washer then, right? That's a washer. Now if this is on the homework and they say you have to use shell method, then you do what I have in the black. But since you're going around y equals 4, vertical strips, which is good because we can keep it solved for y. The outer radius is 4 minus 0. The inner radius is 4 minus x squared, top minus bottom. And you just, there it is. Right? Now, a few people are having trouble getting their parentheses in the right place, whatever. You got to be careful with the pi. Keep the pi on the outside, otherwise you got parentheses around this whole thing inside here. That goes from 0 to 2. The red strips would go from 0 to 2. The black strips, for your shell method, now notice it's 4 minus y, so this strip is y. So if this is down here at 1, 4 minus 1, it's 3 away from the center. So 4 minus y is your p. 2 minus square root of y is the right minus left. This x coordinate minus that x coordinate. So you got to solve it correct. So you do that. 0 to 4. The black strips would go from 0 up to 4. 2 pi out in front. Get the same. Was it over 15? Is that right? 224 pi over 15. So both methods perfectly fine. Whichever one, and neither one was very difficult, I don't think, to set up. Just two different ways of doing it. Adding up the volume of the layers, adding up the volume of the slices to get the volume. All right. So your homework is right there in the LH packet. The first 4, like I said, the first 4 are just single problems. I've got the answers up here if you want to check to see if you get off to a good start. But they're just single problems. Use the shell method. On 21, it's one of those where it's 4 parts. They give you 4 different things. They give you a region. They give you 4 different places to revolve. It says use disc or shell, whichever you prefer. And do both if, just for practice, whatever. It's up to you. But they've got, the answers are in the book up here. Whoops, sorry.